All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions. You can actually, the speaker today wants to do this interactively on the fly, so you're welcome to do so. All right, today's DDPS seminar is open to external audiences, and so no classified discussion. And finally, the talk today will be recorded and uploaded in our YouTube channel. So that's about it. Now let me introduce our speaker today. It is an honor to host Professor Floryan, who is the Kelsey Assistant Professor of Mechanical Engineering at the University of Houston. He received his the bachelor's degree in science in mechanical engineering and BA degree in economics from the Cornell University, and his master's and PhD degree in mechanical and aerospace engineering from Princeton University, where he graduated as the Porter Ogden Jacobus Fellow. His research is at the intersection of fluid mechanics and nonlinear dynamics, with interests in bio-inspired locomotion and using data to model and control dynamical systems. Today, Daniel will give a talk about charting dynamics from data. Please expect a wonderful talk and enjoy it. Now, without further ado, let me pass the baton to Daniel by asking our usual question. That is, what is your favorite things to do other than research?
Oh, well, I really enjoy playing basketball, watching, playing basketball, everything about that. So, yeah.
Wow. Okay. So the NBA playoff is going to start soon. So
Yeah,
I guess
I
you're
just
following that.
just another week or so left, so I'm excited about that as well.
Wonderful, wonderful. Okay, the stage is yours.
Okay, thank you, Youngsu, so much for the introduction, and thank you everyone for joining me today. So today I'm going to be talking about something that I'm calling charting dynamics from data, and we'll see exactly what that means. But before getting to the talk, I just wanted to say a little bit about myself and the group. So I just joined the University of Houston this past October, and so my group is brand new, and we're just really starting out our own research. And so I want to say a little bit about exactly what we do. So my website is listed up here, dfloryan.github.io. And if you go there, you'll see some of the things that we're interested on. So Youngsu mentioned we work at the intersection of fluids and nonlinear dynamics with interest in bio-inspired locomotion, learning structure and complex systems, as well as how fluids and thermal effects interact, especially in environmental contexts. And we're looking for people, both students and postdocs, to join. And I'm really keen to talk to potential collaborators and people who just work on interesting things, as I'm sure everyone in this audience does. So if anything today is even of a little bit of interest to you, please do reach out to me. I have my email up here, and I'll also have it up on the screen at the end of the talk. Okay, so just before getting started, I also want to acknowledge Mike Graham from the University of Wisconsin-Madison, who is collaborating on this work, as well as the AFOSR and ONR for funding this work. So today's talk is going to be all about dynamical systems in a very broad sense. And dynamical systems, of course, are fundamental to our ability to model processes in engineering and the sciences. And just a couple of examples that I'm sure we're all familiar with are, for one, Newton's second law, right? So using Newton's second law, we can derive governing equations for how objects move. An example that's become more prevalent in the last few years are SIR models to model disease spread. And of course, there are many more examples where we use ideas from dynamical systems to develop models of the real world and the manufactured world as well. So dynamical systems are very useful for understanding nature and the things that people construct, but there are a number of challenges as well. For one, governing equations might be unknown or only partially known. And it might also be the case that we don't even have recourse to first principles to actually derive equations of motion. Beyond that, we might have very nonlinear behavior. And even if we can derive equations, the systems that we get might be so high dimensional to the point of being difficult to analyze and prohibitively expensive to make predictions with. And something that I think is really emblematic of this is, well, here's a mesh of a global climate model. And you can see just how enormous this system will be, how many degrees of freedom it will have. And actually, trying to make predictions with this is incredibly expensive and prohibitive to do, basically. So even in the face of these challenges, what we often do have recourse to is data, and it's often very rich data. And so can we somehow use this data to ameliorate some of the challenges that we face? And this motivates the sort of main theme or goal behind today's talk, which is to develop simple dynamical models directly from data. And the emphasis here is on simplicity. Okay, so this alone and the fact that we have data doesn't really immediately solve the challenges that we face. Data can still be very complex. It can reflect very complex behavior, and it can also be very high dimensional. But what we do know is that there are these key enablers that are present, which is that patterns often exist in data, especially data that comes from dynamical systems. And a really neat example of this is shown in this movie here. So this is a movie taken by a satellite of the flow over the island of Guadeloupe. Okay, so we see cloud coverage over the island, and there's wind blowing from left to right. And we see the emergence of these large-scale patterns. Right? We see vortex shedding behind this entire island. And these sorts of patterns enable low-dimensional representations of our systems and thereby allow us to develop simple dynamical models. Okay, so we have dynamical systems that might be very complex and high-dimensional, and patterns exist in them, but how do we use this sort of information to get by the challenges that I mentioned? The reason that patterns emerged is because natural systems tend to live on small or low-dimensional manifolds. Okay, and I mean manifolds in state space. So here's the picture that I want you to keep in mind. Say that we have a very high-dimensional state space, and we fill that with a bunch of particles. So each particle here represents a possible state of the system. And as we let these particles move under the dynamics, then what we see oftentimes is that very quickly these particles become attracted to a subset of this state space, or in this case, become attracted to this donut-shaped manifold. Okay, and this is even true for infinite dimensional systems like the ones that we get from PDEs. And the mechanism that makes this happen is dissipation. So when dissipation is present, there often exists a finite dimensional attracting set that's called an inertial manifold. And this inertial manifold is where the long-time dynamics live. Okay, and in some cases you can formally prove that this exists, and in other cases we sort of implicitly assume that this is something that exists. So now that we have this picture in mind that dynamics are attracted to it and eventually live on these lower dimensional manifolds, we can go back to our original goal and make it a little bit more precise. Okay, so the way that we're going to attain this goal is by a two-step process. First, what we'll do is find the manifold where the dynamics live. Find this lower dimensional set embedded in this very high dimensional space that everything is attracted to. And the way that we'll do this is by learning a coordinate transformation from the high dimensional coordinates to the low dimensional coordinates that are valid on the manifold. And these low dimensional coordinates can be thought of as the essential dynamical variables. Now, once we have this manifold in hand, then what we can do is learn the dynamics on the manifold in the low dimensional coordinates. And this will give us a low dimensional, ideally minimal dimensional model for the dynamics of our system. Okay, so this is what we're going to do, and I guess a natural question that arises is how do we actually find this manifold? What's a way to do it? What's the best way to do it? What should we do? So there are many ways to learn a manifold. I've listed some of the nonlinear manifold learning methods here that are quite popular. So kernel PCA is one, isomap, locally linear embedding, Laplacian eigenmaps, Hessian eigenmaps, t-SNE, autoencoders, and there's a very large list of these sort of methods. And intuitively, intuitively, the way that we think of a manifold is as a sort of curved surface that's embedded in a volume. So I'll be using this donut here as a representative of what a manifold is. We have a surface of a donut, this curved surface that's living in three-dimensional space in this case. And the way that all of these manifold learning methods work, at least intuitively, is that they basically all try to flatten a manifold, right? You take something curvy and you try to make it flat or Euclidean. But what you'll find with any of these methods is a problem, which is that the mappings that they produce are not injective. And here's what I mean by that. Let's say that we look at this torus manifold on the right, and let's color the top half red and the bottom half blue. So we know that this torus, the surface of it, is two-dimensional, right? It's just a surface in a three-dimensional space, and so we should be able to come up with a two-dimensional representation or reduce this torus to a two-dimensional space. And so all these manifold learning methods, they try to flatten this torus, and what you'll find is no matter which way you try to flatten this thing, it'll collapse on top of each other. And what happens now is that you can no longer distinguish the top from the bottom. You can't distinguish the blue from the red. And so since you can't distinguish the top from the bottom, the blue from the red, you can't recover the torus from this flattened annulus now, okay? And so in trying to reduce the dimension here, we've actually lost information. This mapping is not injective. It's mapped different points to the same points, and we have no way to recover our original object. So to figure out how to actually counter this problem, we'll have to understand manifolds a little bit more deeply. Okay, so what is a manifold really? Our working representation of a manifold will be...
Daniel, there's a question by Pat, and he asked about, are you assuming the manifold can be described as a set of simple equations or in a more complex way, say using locally weighted regression?
I'm just assuming a manifold. I don't necessarily need an equation. I think the next slide, this coming slide, will actually
Good to go. Yeah.
say what I mean by that.
Okay.
Yeah, and if not, then we can keep going with the question. Okay, so the way that we're going to think of a manifold is as what's known as an atlas of charts. So there are two key words here, an atlas and a chart, and I'll explain what each of those means. So a chart is something that has two ingredients. The first ingredient is called a coordinate domain, and what this is an open subset on the manifold. Think of it as this little red patch of this torus here. And then the second ingredient is something called a coordinate map. And what this is a continuous and invertible map that takes us from the coordinate domain, from this red patch, to a subset of Euclidean space of the same dimension as the manifold. So here we're taking this patch that's embedded in three-dimensional space and mapping it to this flat two-dimensional space. So the way to think of this coordinate map is as something that takes a patch and then flattens it. Okay, so that's what a chart is. And then an atlas is just a collection of charts that together cover the entire manifold. So in addition to this red or pink one, I can have a blue one, and I can keep adding more and more until I've covered the entire manifold. Okay, and what will be especially relevant for us, since we're thinking about dynamics, is as your state is evolving along a manifold, you might move from one patch to another. And so what we'll have to be able to do is come up with a way to transition between these low dimensional patches, between the flat red patch and the flat blue patch. And we can do that by composing these coordinate maps and their inverses to transition between these low-dimensional representations. Okay, so the way to really think of a manifold is as a collection of patches that can together be flattened. And this sort of representation is minimal dimensional. So if you don't use patches, if you just try to flatten the entire thing at once, then you cannot get to the true or the intrinsic dimension of a manifold. So let's go back to our torus example that we tried to unsuccessfully flatten before. And what we'll do now is, before trying to flatten this thing, we'll first break it up into a collection of patches. Okay? Then we separate each patch. And now that we have each little piece individually, we can flatten these no problem. Nothing collapses on top of itself. We now have local two-dimensional representations of each patch, and we can invertedly go back to our curved manifold. So this is how these ideas work. And the next question is, how can we actually implement this sort of approach when all that we have is a collection of data? So the way that we implement this is as follows. Okay, so what we're going to assume that we have is time series data. It can either be one long time series or several sets of time series. And we'll assume that the data lie on or near a manifold, and then we follow a three-step procedure. In the first step, we cluster the data into overlapping patches. And this gives us our overlapping coordinate domains. So for everything that I'm showing today, we've used k-means and then an additional procedure to make the resulting clusters overlap. So when we cluster our data, we sort of implicitly build these patches. So once we have these patches, the next step is to learn how to flatten each patch. Okay. So for each patch, what we'll do is we'll approximate the coordinate map that I mentioned. And this is the coordinate map that takes us from high dimensional space to a low dimensional space, and we'll approximate it using the neural network since we have these universal approximation theorems or properties. And we simultaneously learn both the neural network, or we simultaneously train a neural network to approximate this coordinate map as well as its inverse. So we can map forward to this lower dimensional space and backward to the ambient dimension. And together, these two neural networks form something that's called an autoencoder, or an undercompleted autoencoder that I'm sure many of you are familiar with. So now what we have is a way to reduce the dimension of our data to a minimal dimension. And now that we have this low dimensional or minimal dimensional representation of data, we can now learn the dynamics in these low dimensional coordinates. So finally, for each patch, we now have time series data in the reduced space, and we learn the dynamics in this reduced space from this time series data. Okay, so the dynamics are still nonlinear in the low dimensional coordinates, and so we will approximate them using neural networks to learn either ordinary differential equations for the dynamics or time delta t flow maps. Okay. And this is our entire method in a nutshell. And really the key here is this decomposition of everything into patches. And I also mentioned that we use autoencoders. So in case you're not familiar with this, I don't know what an autoencoder is. It basically tries to take an input and reconstruct it as perfectly as possible, but with a bottleneck in the middle to get sort of the basic representation of what your object is. Okay, so to show how these things, or how this method works, I want to take you through a handful, or I guess more than a handful of examples, and we'll start with something really simple and then in the end get to something that's quite complicated. So for the first very simplest example, I just want you to think of a particle that's moving around in a circle. Okay, so we just have a particle that's moving at a constant speed around a circle. And our data consists of 40 points equally spaced around the circle, and we have x and y coordinates for each point. So our data is two-dimensional since we have the x and the y coordinates, but we know that a circle is really a one-dimensional object, right? It's just a curve that connects to itself. And so we should be able to get a one-dimensional dynamical model, since this is a one-dimensional manifold that this data and the dynamics live on. And so let's see how everything works. So just following our procedure, the first thing that we do is break this data up into patches. So in this case, we've broken it up into 3 patches, a red one, a blue one, and a yellow one. And then we also make sure that these patches overlap. We then take each of these patches, or the data in each patch, and we train autoencoders to find reduced representations of the data here. So we can map invertibly back and forth from this 2-dimensional ambient space to a 1-dimensional latent space. And in principle, this is lossless. In principle, we can do this without losing any information. And finally, once we have our data in the 1-dimensional space, the reduced space here, then we can train our neural networks for the dynamics in these reduced spaces. So once we have our local dynamical models, we can then patch them all together to get global dynamics for the system. And let's see how this works. So in this last plot here on the right, what I've done is just taken an initial condition somewhere on the circle, map that to the low-dimensional, the 1-dimensional space, and then evolve the state of the system using our learned 1-dimensional dynamical model. And so what we see are these points. So the points come from our trained dynamical model. And if you can see, there's a gray curve on top of these points. And if you can't see it, then you'll just have to trust me that there's almost a perfect overlap between our trained dynamical model and the true dynamics of the system. And what I want you to notice especially is that we have these smooth transitions as we go from one patch to another. So as you change from yellow to blue, from blue to red, and from red to yellow, we see very nice smooth transitions. So on the top plot, I've just shown the first cycle of the motion. And then on the bottom plot, all the way down to 1,000 time steps out of the motion. And so we get this really nice high fidelity model. You can see that maybe the phase speed is a little bit off, but that's to be expected and can be improved with further training, for example.
Hey, Daniel, there is another question by Pat. He asked, how many samples do you need for these simple examples? I'm guessing the sample complexity will be much higher for harder problems.
Yes, so I guess you need to cover your manifold. That will scale with the dimension of the underlying manifold. Right, so even if you have your ambient space is very high dimensional, but your manifold is low dimensional, then the sample complexity should scale with that intrinsic dimension of the manifold.
But since you don't know the underlying dimension of the...
Yeah, so that's that's a tricky thing. So you don't know beforehand the answer.
Oh, right. All right. Sounds good.
Okay. So this is how things work for the very simplest example that I could think of. And now let's make
sorry. Pat asked, how many samples do you need here for this specific example?
Okay, in this case, 40 samples, but I think you could get away with less, but that's what was used here.
Okay,
so it was 40 samples, which was one rotation around the circle.
Okay, got it.
Or one revolution around the circle.
Okay.
Okay, so let's make things just slightly more complex. And now we'll have a particle that's moving around the surface of a torus, and it moves periodically. So it forms this little coil around the surface of the torus, and it has this periodic orbit. Okay, so it's basically the same thing now, except we have an orbit that's a little bit more complicated, and the ambient dimension is 3. But again, this is a periodic orbit, so we know that we should be able to find a one-dimensional representation. This is something that's still topologically a circle, so we should find a one-dimensional representation. And we just follow our procedure exactly like we did in the last example. So we break our data up into patches. Here again, I've used 3 patches, a red one, a blue one, and a yellow one. We then take each of those patches and independently learn how to reduce the dimension to 1, since we know that we should be able to do that in this case. And now that we have our time series data in the reduced spaces, we again learn dynamical models in the reduced spaces. And let's see how this works. So again, we take an initial condition and evolve it forward in time using our learned dynamical model and compare it to the true dynamics in the gray line. And again, we see that we have very good agreement. So on the top, I'm showing the first period, and on the bottom up to the 10th period of motion, and we have very good agreement. I think I'm seeing other questions pop up.
Yeah, another question by Jack. How does this approach work for non-integrable systems? That is, system has no period.
Okay, I will show you something that does not have a period.
Great.
Any other questions?
No, it's just comments, not questions.
Okay, sure. Okay, so let's go a little bit more complicated now. So now we're going to have still a particle moving around the surface of a torus, but now the periods of motion in the toroidal and poloidal directions are incommensurate. So we no longer get something that's periodic, we instead get something that's quasi-periodic. And if you let this particle move forever, it'll densely fill the surface of this torus. Okay, so now we have something that's living on the surface of the torus. Not only the data is three-dimensional, but we know that we should be able to find a two-dimensional representation since it's on the surface of the torus. And so what we do is we split our data up into these patches again. So this time I've used 6 patches. There's a red one, a blue one, and a yellow one at the top, and then green, purple, and orange on the bottom. And then in the bottom left, I'm just showing how we make these different patches overlap with each other. And you can see that several points are actually members of several patches. But once we have that, we can then separate all the patches, and then we can learn how to map each patch to a low-dimensional, in this case, two-dimensional space. And we do that using autoencoders to invertibly make that mapping. And again, now that we have our data in this low-dimensional space, we learn the dynamics in the lower two-dimensional space, and then we can see how this compares to ground truth dynamics. So again, we take an initial condition that's on the surface of our manifold, we evolve it forward in time using our learned dynamical model, and compare that to the true dynamics. So the top 2 plots on the right here, those show the X, Y, and Z coordinates. So the points show what our model gives, and then the gray lines show the true dynamics. And then on the bottom 2 plots, I've reconstructed the 2 angles, since that might be easier to interpret. And you can see that we're doing quite well. The phase speeds are a little bit off, so you can see that in the bottom right plot, right? How the points are a little bit shifted away from the gray lines. But overall, this is, we're very happy with the sort of reconstruction that we can get. And the key point here is that we're getting something that's minimal dimensional. So if you don't do this sort of decomposition into patches, you will never be able to get something that's two-dimensional.
Is it, well, okay. Another question from me: how many how do you know how many patches do you have to use?
Okay, yeah. So I can tell you for a torus, you would need, let's see, how many would you would need at least 3 patches for a torus. Now, this is sort of a tricky thing. You don't know beforehand how many patches you actually need. Okay, so that's highly dependent on the geometry of your data. And so in general, that's something that you would have to sort of empirically figure out. There may be smarter ways to figure out how many patches you need. So I know that there's an ever-increasing set of tools for trying to figure out the geometry of data sets. So tools like that could potentially provide some sort of insight into how many patches you need. But in general, you don't know beforehand. Now, what you could do is just start with many patches and then sort of iteratively reduce the number of patches that you get. And at some point, you won't be able to map to a low dimension anymore. Okay, so the nice thing about these manifolds, or the manifolds that come from dynamical systems, is that the dimension of it is a global property. So that means that each patch has to have the same dimension. And so you could just sort of figure out the dimension of just one patch of the data and use that to judge whether you can decrease the number of patches or not, and whether you can decrease the dimension of the system or not. So you can sort of figure things out locally and then apply that globally.
All right, sounds good.
Okay. So let's again move to a slightly more complicated example. So here we're going to be dealing with a reaction-diffusion system. So this is given by two PDEs for two fields, U and V. It looks more complicated than it is. It's just a diffusion term on the right of the equation, and then a cubic nonlinearity for the other terms. And under the right conditions, what you'll get is a nice spiral wave that forms. Okay, so if I play this animation, these are the sort of dynamics that you get from this reaction diffusion system, just this nice periodic wave that spirals out. Okay, so I showed two movies here, right? One on the left and one on the right. So the one of them is from the data, and then the other one is from our learned model. And if I play it again, I think you'll have a hard time actually distinguishing which is which. So it turns out that the one on the left has a dimension of a bit over 20,000, and the one on the right has a dimension of 1. And this is the sort of reduction that you can get by using this patching approach. So again, we patched the data up into separate patches and learned local dynamical models for each patch, and then sewed everything together to get these global dynamics that I showed in the animation here. Okay, so that's just to show that this works, I guess, not surprisingly, in higher dimensions as well. So let's start to get a little bit more complicated. So we can basically do the same thing for other PDEs. So here's the Kuramoto-Sivashinsky PDE. It's, one of its uses is to model flame front dynamics, and you can get a very nice rich set of dynamics from this PDE. So here's another example where we have just some simple periodic dynamics. Okay, so this is the data that I'm showing now, and the colored bars up top show how we've patched this into 3 patches in state space. This is the reconstruction, so we can map things to 1 dimension since we know this is a 1-dimensional manifold. The reconstruction is very good, and if we look at the evolution of an initial condition using our learned model, we see basically very high fidelity behavior that's almost perfectly matches what you would get in the true dynamical system. Okay, so this is still periodic, so it's not, I guess I lied a little bit. This wasn't more complicated than the previous example, but this next one will be. So now we're going to look at the chaos equation, but we'll change the hyperdiffusion coefficient so that we get dynamics with disparate timescales. Okay, so here I'm showing just a heat map. Okay, so the vertical coordinate that's the spatial coordinate, and then the x-axis is that's just time. And what you can see is this very slow drifting behavior, right? And this longer plot is over 100 time units. And if I zoom into 1 time unit, which is this plot on the upper right, you can see these much faster beating dynamics. Okay, so we now have these disparate timescales that are a factor of 100 different. And what we do in this case is we actually know that there's a symmetry present in the system. There's a translational equivariance in the system. And so what we do is we factor that symmetry out by separating this data into a shape variable in the middle here, and then a phase variable on the bottom. Okay, so when we do this, the shape variable, now that's just something periodic or quasi-periodic. And the phase variable, we have this periodic behavior, again, with this slow drift as well. Okay, and so what do we do now? We take 1 time unit of the data That's what we use to train, okay? So one time unit is enough to capture the fast beating dynamics, but it's a very small fraction of this sort of slow drift period. But nevertheless, we'll just use one period of data for our training. We can again map this to one dimension. And then when we reconstruct things, we see that we're actually able to get these fast beating dynamics on the bottom right, as well as these slow drifting dynamics in the middle here. So even though we've only used one time unit of data, we nevertheless capture both of these features. Okay, so I have one last example that I want to show you, which has the most complex dynamics of all the examples. And we're still going to be dealing with the KS system, but now it'll be in a regime where we have intermittent dynamics. So what the space-time plot looks like is this. So as you move from left to right, as you move forward in time, you sort of go from these almost quasi-steady or quasi-stable cellular states, and there's a very fast burst onto another sort of quasi-stable cellular system. And you sort of burst back and forth between these cells. If we look at a state space projection of this, then we'll get a little bit more intuition for what's going on. Okay, so I'm going to take this data, and just for the purpose of visualization, I'll project it onto the leading 3 Fourier coefficients. And when we do that, these are the sort of dynamics that we see. Okay, so the red point is showing the dynamics, and this blue skeleton is showing the manifold that we're evolving on. And what you see is that we burst between these two saddle points on the left and the right. And when we're bursting, it's basically randomly choosing which of these branches it's bursting along. So we have these complicated non-periodic dynamics now. And again, some of the key challenges here is that we have disparate timescales. We have these fast bursts in between these quiescent cells. There's a very thin state space structure. It's cage-like, I would say. And we have very sensitive non-periodic dynamics. So this is going to be something that's quite challenging to capture with a low-dimensional model. Okay, nevertheless, we move forward. So we take our data. In this case, we patch it up into 6 patches. The way that I determined the number of patches to use in this example was by looking at that projection that I showed on the last slide. So we saw this sort of cage-like structure. And so we decided to patch it into 6 patches, 1 for each of the saddle points, so red on the left, blue on the right, and then another patch for each of these heteroclinic branches that connects the saddle points. Okay. And so we follow our same procedure to learn an atlas with 6 charts. And I should also mention that we use this sort of special method from this paper in PRE from Leinen and Graham to actually train our autoencoders, where we use it's like a combination of PCA and neural networks to get a special autoencoder structure. But in the end, what we're able to do is get this atlas with 6 charts, and we can get a 3-dimensional dynamical model that's very qualitatively correct, but a little bit off quantitatively. Okay, so we see a qualitatively correct minimal dimensional model, but there is a quantitative discrepancy in the length of the quiescent periods. So you can see that we don't stay on the cells for as long as we do in the true dynamical system. But this is something that we believe is actually inherent to the system itself. So there's a logarithmic divergence that's associated with these 2 saddle points. And so this is something that would be difficult to learn for any model, not just the one that we've developed here. But in any case, you can see that we're certainly getting the right behavior. We have the space state structure looks correct. And if you look at the statistics that you get from the system, it's also correct. Okay. And so I think a really important question to ask is, how does this actually compare to previous methods? And so here, there's actually some theory that becomes very relevant. So there's a theorem that's known as the Strong-Whitney embedding theorem. And essentially what it tells us is that if you don't use an atlas of charts, if you don't break things up into patches, you should still be able to reduce the dimension to 2n in the worst case. So in this last example that I showed, where we believe that the true dimension is 3, if we don't break things up into patches, we should still be able to reduce the dimension to 6 and capture the same sort of behavior that we're able to capture with our minimal patched model. But when we actually try to do that and train a 6-dimensional model just using a single autoencoder without patching things up, what we find is that we get something that isn't even qualitatively correct. So what we get is something that's just attracted. It has this attractive fixed point that's not even on the manifold that the data lives on. And if you look at the reconstruction error that you get using this 6-dimensional no chart model versus our approach where we're patching things up, then you see that our approach consistently gets an order of magnitude better reconstruction than if you use no charts. And in particular, the comparison that you should be making is the 3-dimensional model that we have with our patching approach versus the 6-dimensional model that you get without using patches. Since Whitney's embedding theorem says that these should be able, in principle, to work to do just as well. But what we see is even when we use 6 dimensions and we use the same number of trainable parameters, we still do an order of magnitude worse when we don't patch things up compared to when we patch things up. And so we're actually getting benefits, practical benefits beyond what you might expect from the theory that's provided by Whitney. Okay, so just to summarize quickly, inspired by differential geometry, we developed this atlas of charts-based approach to learn simple, so the simplest dynamical models directly from data. And our approach, it works by learning a patchwork of local models and then sewing them together to get global dynamics. And we've seen that this is able to outperform global methods, even give us something reasonable where global methods just fail completely. And I'll just close by noting 3 major benefits of this approach. So the first one I've been sort of harping on the whole talk, which is the ability to obtain dynamical models of the lowest possible dimension of the intrinsic dimension of the system. The second is the sort of divide and conquer approach leads to computational benefits that include scalability, the ability to adapt models locally, and an algorithm that's embarrassingly parallelizable since all the patches are treated independently during the training phase. And also, this has the ability to separate state space into regions of distinct behavior. So you might have, like in a turbulent bursting system, for example, you might have regions of state space that have widely different behavior. And so it could be advantageous to have different models for each of those different regions and then sort of patch them together. And just as a final note, even though we've used neural networks here, at least from a practical standpoint, you can just use any other regression approach that you like. So neural networks aren't necessarily required to make this work. Okay, so with that, I'd like to thank everyone for listening to my talk, and I'm very happy to take any questions that you might have.
Thank you so much for the wonderful talk. Indeed, there is another question by Pat. He asked, have you compared your approach to methods that include governing equation directly? There has been lots of work on that.
Sorry, could you repeat that again?
Have you compared your approach to methods that induce governing equations directly?
So maybe Pat could tell me what sort of methods you have in mind.
Well, sure. So there's been 40 years of work on trying to discover laws, numeric laws, and models from data stated in established scientific formalisms. But just in the past 6 years or so, there's been a bunch of people that started working on this, right? And so they have data, often time series data, and the output is a set of equations that describe the dynamics. And that sounds like you said you compared your approach to global methods, but and these are certainly global methods, but it doesn't sound like I didn't hear you say that you were comparing to these techniques. So rather than building a bunch of local patches, you come up with one set of laws that describe everything. For example, for your simple circle example, you would discover an equation or a differential equation, set of differential equations that describe the change.
Or you could use existing equations if you happen to know those.
Of course, if you know them, but there are well-established techniques for discovering them from the data.
Yeah. So the key distinction is breaking things up into patches, and that gives you the ability to get the minimal dimensional system that you possibly can. So that's really the only distinction. You can use actually all these other methods.
My question is I don't know if you mean what you mean by minimal here, because if you come up with, like, say, two equations to describe the circle, you don't need patches at all, right? There's one patch.
Yeah.
And so when you said that you compared your approach to global methods, it sort of sounded like you were talking about that, but I don't think you were. Is that correct?
No, that's correct. So you're right. You can come up with a system of two differential equations for the circle, right? But you cannot come up with a system of one if you do everything at once, if you treat the circle as a whole.
Oh, I see.
So the point here is when you break it up into patches, you can come up with a one-dimensional system instead of a two-dimensional system.
And why is that more desirable than having two simple differential equations?
Yeah, so in some cases, you can get drastically better performance by getting something that's lower dimensional. So in this last example that I showed, actually, right, where I had this sort of bursting behavior, there we got something qualitatively correct with these local three-dimensional models. Whereas when we try to just learn a set of 6 differential equations for the entire data, for the entire data set or for the entire system, even though in theory that should have worked, it actually failed completely and gave us something that was even qualitatively off.
Okay, I think I understand now what you're talking about. You're claiming that in some cases there are hidden variables that could describe systems in a smaller number of dimensions than even the equations themselves. Okay. Now you may lose interpretability in the process, and that may or may not be a price you're willing to pay. That's okay. I just wanted to understand what your position is, and I do understand it now. Thank you. Yeah. I also put a bunch of links in the chat box about locally weighted learning, local linear regression. This is very similar in spirit to your approach, except that it doesn't require you to identify patches. What happens is each time you have a new test case, you find the nearest n points, and then you do local regression on those points. And I do think that you will want to compare your approach to that. It goes back to the mid 1990s, and there's a survey paper that I put in the chat box that's worth pursuing.
Okay, yeah. So I have seen, I can't see the links right now, but I have taken a look at some of these works from the 90s. And one thing that I've seen basically in all the ones that I saw that do these sort of local models is that even though they treat things locally, implicitly they still try to build a global coordinate system from these local models. So there's one work from Brand, for example, who's the first person to mention analysis of charts. And so even if you treat things locally, but still try to get a global coordinate system in the end, you fall into the same problem that you do with these global methods.
Well, I think the standard story would be that they are creating a lower dimensional manifold through the space by doing this. But I grant you that there's a sense in which they certainly aren't inferring the latent variables that you are. So I agree there's a difference, although hearing your talk the first time, that was the first thing that leapt to my mind. And I do think you want to make sure to distinguish your approach from that, because it superficially seems very closely related.
Yeah. Okay, fair enough. I know what you mean, and I'll take a look at those papers. Thank you.
Thanks.
Sounds good. Is there any other questions from audience? Okay, from Scott. Okay, there's another. Okay, so the first question from Scott. How robust is your method to noise in the data?
Yeah, we haven't checked this explicitly, but it would be as robust as any autoencoder model is. The one thing that will be a little bit tricky is in transitioning from one patch to another. So if you have noisy data, then you're probably going to get, where the two manifolds intersect, the disagreement will probably be higher when you have noisy data. And so when you transition from one to another, you might get something that's not smooth there. But otherwise, you inherit the same properties that autoencoders have.
All right, sounds good. Another question. I think I missed the question. One question before. Right. Question from TS. Can you give some intuition as to why k-means is the right way to cover the data with patches, since k-means is used to optimize an objective that may have little to do with the right way to determine the patches?
Yeah, that's a fair question. And I make no claims that k-means is the right way to go. It's a convenient thing that should scale well. And that's the main reason that we used it. But there could be much better ways to actually come up with how to come up with a decomposition into patches. I'm actually very interested in what could be better ways to do that. So very happy to hear any comments or suggestions if someone could email those to me.
All right, sounds good. Okay, great. Another question from Harshit. Thank you for the nice talk. Can you provide more details about transitioning from one patch to another? How is the transition constructed, and how do we detect when one needs to go from one patch to another?
Yeah, okay. So the way that we've been doing it so far is when we perform our initial decomposition into patches, each data point is uniquely assigned to a patch, right? So k-means uniquely assigns each point to a cluster. And then we do a little procedure where we start to make these patches overlap with each other. So when we do that, there are points now that might belong to multiple patches. And so here we develop a notion of internal points and boundary points. So a data point is internal to a patch if it was assigned to that patch during the initial clustering procedure. A data point is external to a patch, or it's on the boundary of a patch if it was assigned to that patch during the overlap procedure. So imagine we start with some patch, it contains some data points, and then we expand that patch outward. During that expansion process, some other points are assigned to that patch, and those points are considered external or boundary points of that patch. So the way that transitions work is as we're evolving our state forward in time, we search for the nearest training point to the current state. If that nearest training point is an internal point, we stay in that patch. If the nearest point is an external or boundary point, then we switch to the other patch. And the reason that we can do that is because a point that is a boundary or exterior point of one patch will be uniquely interior to a different patch. And so we know that we should be switching from one patch to another. So I don't know if that helped, but we do have a preprint that sort of explains it in more detail as well. But that's how we do it.
Sounds good to me. Okay, another question from Chol Wu. He asked, can the patching approach be used to capture behavior dependent on the long range order? Not sure what he means by long range order, but what do you know?
I'm not sure either.
Hey, Chol Wu, would you clarify your questions?
Sorry, I meant like, can the patching approach be used to capture the dynamics that is, I guess, pervasive globally? Like, not just local behavior, but like the global behavior.
Do you have an example in mind?
So I guess for example, I don't know if this is really relevant, but like I'm from a chemistry background, and if you do like molecular dynamic simulations, sometimes the behavior of the atoms they're governed by a long range governing
I see.
type of
Okay.
equation. So I was wondering if the patching approach can be used to like capture those kinds of dynamics.
Yeah, in principle, yes. So the patching is done in state space, and what you're describing are these long-range interactions in physical space. Okay, but everything done is done in state space, so that should this method should be able to capture that, and then any other method should be able to capture that as well, as long as it's in state space.
All right, sounds good. I don't see any other questions now. Is there any other questions? If not, we can thank our speaker today for the wonderful talk. It was really interesting talk. So I would like to have a, the follow-on the meeting with you personally. But other than that, thank you so much, Daniel, for the wonderful talk.
All right. Thank you, everyone.
All right. Thank you, everyone, for joining today.
Okay.